Hello everyone. Our project title is Build Real-Time EV and ADAS Warning System. So we have done this project under the Emertex um, company, and we have done this project in a group. So my group members are Sakshi Todkar, myself Aditi More, and Samprada Hirema. We are from BTech ENTC in the Government College of Engineering, Karad. So this is the project which basically shows or based on an embedded system and automotive technology. We developed a prototype using a STM32F10 3C866, which is a blue pill microcontroller, to monitor vehicle parameters which are important like speed, battery level, temperature, and obstacle distance. The system also provides warning messages to improve the vehicle safety. Our project combines the concept of EV and ADAS. So what is meant by EV and what is meant by ADAS? We will see. So first is, what is EV? EV is nothing but an electric vehicle that runs on an electrical motor instead of petrol or a diesel. The motor gets power from the rechargeable batteries, and which is environmental friendly. So these are some important features of the EV. So first is battery powered operation, which is nothing but or which tells us that the vehicle uses rechargeable lithium ion batteries as the main source of power. The second is electrical motor for propulsion, means the battery supplies the electrical energy to the motor, which converts it into the mechanical motion to drive the vehicle. Then next is the tailpipe emissions, means it gives a zero emission. Since there is no combustion engine, harmful gases like carbon dioxide are not released by the vehicle. So which is the environmental friendly also, means it gives a zero emission. Second is quiet and smooth operation, means electric motor produces a very little noise compared to the petrol engines. Then fifth one is instant torque and fast acceleration, means electric motor provides maximum torque instantly, resulting in a smooth and fast acceleration. So these are the features, as well as there are some advantages also. That means it is environmental friendly, it requires a less maintenance, and it has a low running cost. The efficiency is also low. Then next we will see what is ADAS. ADAS is a advanced driver assistance system, which is basically a ADAS, which is it is a collection of technologies that helps the driver to drive more safely. Means ADAS uses the sensors, cameras, ultrasonic sensors, and more type of sensors also, and software to detect the obstacles and warn the driver. So there are some features of ADAS also. First is collision warning. What is ADAS gives is that is collision warning, means if an obstacle comes to close, the system alerts the driver that we are get to collide. Then next is automatic emergency braking. If a driver does not react in the time or not able to react in the time, the system can automatically apply the brake and the vehicle can stop. The next is lane departure warning, means it alerts the driver if the driver has leave its lane. Means if driver is not on a proper lane, it will give alert to the driver. Then adaptive cruise control, means it automatically adjusts vehicle speed according to the vehicle ahead. Means in front of the vehicle is there, so it will adjust its speed according to that vehicle. Then next is blind spot detection, means it will detect vehicle that cannot be seen in the mirror, which is the most important parameter, because in rainy days we are not able to see the vehicles which are back side or front side, so that ADAS will help us to see that. Then next is parking assistance, means it helps the driver during the parking. Means parking is much a issue nowadays, because there are some less space for the parking. So it gives a savvy. They use some sensors that will assist the driver to park. Then next slide is objectives of the project. So what are the objectives of the project? Is first is to develop a real-time EV dashboard monitoring systems. So means the objective of the project is that we want to develop a real-time EV dashboard on which we can show all the parameters and important parameters on the dashboard, so that driver can easily see that. The second is to provide basic ADAS features for collision avoidance. Means the system warns the drivers whenever an obstacle is detected, so that many accidents can be controlled. Then next is to display vehicle parameters. So there are various parameters of a vehicle that we can display on the dashboard, like speed of the vehicle, battery percentage of the vehicle, then temperature, and the distance from obstacle or distance from the other vehicle is also shown on that dashboard. The fourth objective is that to simulate a EV and ADAS system using STM32, that is microcontroller board. So we have used here the STM32, which is nothing but a blue pill microcontroller to simulate the complete system using a Pixing lab. Second, last one is to improve the vehicle safety. So by the implementation of this real world EV dashboard, we are able to improve the safety. Means whenever dangerous condition occurs, the system immediately gives the warning alerts. Then, so these are the some objectives of the project, that why we have built this EV and ADAS project. Then on the day one, we have introduced to this project by the Vijaya Lakshmi ma'am. So first is introduction. So on the day first of internship, we learned about a complete roadmap of this project. So we understood that what is the electrical vehicle, what is ADAS, basics of EV and basics of ADAS, then what is the automotive embedded system, and what is the STM32 Cube IDE board. Then Pixim Lab is what is Pixim Lab. So and how we are going to implement this on the Python setup. So uh, first is what is the STM32 Cube IDE. So Cube IDE is the used to write for writing, compiling and debugging the embedded C program. Then second is the Pixim Lab. Pixim Lab is used for simulating the STM32 because we have not used any hardware here. So for testing the program without any hardware, we have used a Pixim Lab. Then next is Python. Python is for developing a real-time dashboard to display vehicle parameters such as speed, battery level, then temperature and obstacle distance. So finally we have installed, so on the day first we have installed all the required softwares like STM32 Cube IDE, Pixel Lab and all, and understood how they work and how to handle them. So by the end of the day, we understood about the basic of EV and ADAS. We became familiar with uh, we have become familiar with some microcontrollers like STM32, F10, C38T6 Blue Pill microcontroller. We learned the purpose of STM32, Cube ID, Pixim Lab, and Python. We understood the overall project workflow and how all the components will be going to work together.
Now, I'll explain the ADAS engine module, which is the decision-making unit of our system. It continuously receives distance data from the front, left, and right ultrasonic sensors and determines whether the vehicle is in a safe or dangerous situation. The first feature is time to collision, that is nothing but TTC calculation. Instead of checking only the distance, TTC estimates the remaining time before a possible collision based on vehicle speed. This provides a more intelligent safety decision. Next, we implemented collision detection with two alert level. A warning is generated when the obstacle is within 50 cm or TTC is less than 3 seconds, while a critical alert is generated below 20 cm or TTC is less than 1.5 seconds. This allows the driver to react before an accident occurs. We also developed a blind spot detection, whether the side ultrasonic sensors monitor nearby vehicle or obstacles. If an object is detected within 30 cm, the system alerts the driver before the changing lanes. Finally, parking assist become active below 10 km per hour. It continuously measures the distance from the nearby objects and helps the driver park safely. Together, these features make the ADAS engine an intelligent safety module. Next slide is about UART protocol and command shell. After implementing the ADAS logic, we established communication using UART. We configured USART1 on the STM32 microcontroller to transmit real-time EV and ADAS data. The firmware continuously sends parameters such as speed, battery SOC, that is battery state of charge, motor temperature, torque, drive mode, and sensor information to the external dashboard. We also developed UART command shell, which allows us to control the system during runtime. Using serial commands, we could change the driving mode, modify speed, reset the system, and simulate different conditions without changing the firmware. Finally, we verified successful data transmission and command execution, ensuring reliable communication between the embedded system and the monitoring dashboard. Next slide is about firmware integration and testing, which is the most important. Once all modules were completed, they were integrated into a single firmware running on the STM32 microcontroller. This included the EV module, ADAS engine, UART communication, timers, and sensor processing. Proper synchronization was maintained so that all tasks executed smoothly without affecting system performance. The integrated firmware was tested under different obstacles, distances, and vehicle speed to verify all safety features. During debugging, timing, and communication issues were identified and corrected. Finally, the firmware was validated to ensure stable operation, accurate sensor readings, and reliable overall system performance. Next is about Python dashboard, that is EV gauges. To monitor the vehicle in real time, we developed a Python-based EV dashboard. The dashboard receives UART data from the STM32 microcontroller, verifies each data frame, and displays important vehicle parameters such as speed, battery state of charge, that is SOC, driving range, motor temperature, torque, power, and drive mode. The dashboard refreshes every 100 milliseconds, providing smooth real-time monitoring. Instead of viewing raw serial data, the graphical interface makes it much easier to understand the vehicle's operating condition. Next is Python dashboard, ADAS bird eye view. In addition to the EV dashboard, we developed an ADAS bird eye view dashboard. It is graphically displays obstacles detected by the front, left, and right ultrasonic sensors around the vehicle. It also calculates time to collision and indicates different safety zones such as safe, warning, and critical. Blind spot alerts and fault conditions are also displayed visually. This provides the driver with a clear understanding of the vehicle's surroundings, similar to the ADAS system used in modern electric vehicles. The final stage of the project was system testing and validation. We executed total 17 test cases covering UART communication, sensor timeout detection, collision detection, blind spot monitoring, parking assistant, and overall firmware stability. Each test case was verified by comparing the expected and actual output. Any issues found during testing were debugged and corrected before final validation. Finally, all observation and results were documented in this test report. This internship provided us hands-on experience in embedded system, STM32 programming, UART communication, Python dashboard development, sensor integration, debugging, testing, and real.
Next we will see the project that we have, a real-time project that we have implemented. For firstly, we are using the STM32 Cube IDE software for our embedded C programming. The version is 1.19.0. So STM32 is commonly called as the blue pill board, which is STM32F10C3C86. It is a 32-bit ARM Cortex M3 microcontroller. The specifications are like its clock speed is 72 MHz, 64 KB flash memory, 20 KB SRAM, and 3.3 volt of memory. While working on the STM32 Cube IDE, we will go on the file new, and in new we have to if you want to create a project, then you go for the STM32 project, and we get a project explorer here. Here I have created the project, that is EV dash, means I have to build a dashboard, so I have given name as a EV dash. Once once that file is saved, we have to select the chip. I have selected here the STM32F103C8T6 T6 chip, which is the blue pill board. Once the blue pill board is selected, we have to set the pins for the configuration. So here the green color shows the pins that they are setted. So one by one we will see the pins. So first is PA0, PA1, PA2, PA3. So these are the ADC pins which is used for the analog input, like for reading the analog values like date sensors data and all, means temperature sensors and this much. So we can see that. So next is the PA9 and PA10. These are the USART pins for which is basically used for the receiver and transmitter pin. Then next is the PA8 and PB6 pin. So these are the timer pins which will help to select the timer and channel. Then PB3 and PB5, PB8, PB9 and PC13. These are the general purpose input output pins which are used to set the pin as the input as well as the output. So then PD0 and PD1 are the oscillator pins which is used to connect the external crystal oscillator, provided an accurate clock for the microcontroller. And then here are the some basic yellow color pin shows are the NRST pin, which is used as a reset pin. Then VDD, VSS, these pins are for the power supply and ground. Then VB80, this pin is the backup battery supply for real-time clock is used. So this is the pin configuration. Once pin configuration is set by these categories, we have to save this, and after saving there is an option of generate code. After generating the code, we will get a main file. In the main file we are able to make the changes in the file according to our need. So I have made the changes according to our guide. So changes are made in the while loop one according to the need of the project. I have here is the print status pin also, in which we are going to print the status of temperature, torque, accelerator, brake, ring. Then we are going to check the left, right and front directions also. So I have here we have implemented that. Then nextly, according to the project, what is required that we have done in this project or in this code. So once the code is done, then go for the EV dash and set and click on the build project. Once the build project is clicked, we will able to see that if there is any error or any warnings there are there in the project, in the program. So no warnings. In the to run the Pixim lab, we are required to get a binary file. For the binary file, to generate the binary file, we have to go on the properties, then go on the settings, means C and C++ build, in that settings, and go on the convert to binary file. Tick this box, and after ticking this box, apply and close. Once we apply and close, go on the AV dash and again build the project, and hence our binary file is ready. And this binary file we can load into the Pixim lab. So this is the all about the STM32Cube IDE software for implementing the embedded code.
Now, I will demonstrate the practical implementation of our EV and ADAS system using Pixim Lab. So the interface you are seeing right now is nothing but the Pixim Lab software. This software helps us to test the STM32 firmware in simulated environment before implementing it on the actual hardware. So now what you are seeing is nothing but it is the Pixim Lab software interface, and on this interface these are some tools on the toolbar like file, board, microcontroller, modules, tools and helps. So let us see this one by one. File, this is the most important operation or the function we are seeing here. Through this only we can load the binary file and we can get the actual output what we have designed or implemented into our system. Next is the board. If we click on this, there are varieties of boards are available, but for this our project we have used blue pill board, and we are seeing this blue pill board is available here. Then this is the microcontroller option. We have used STM32F103C8T6 microcontroller. Then in modules, we get two options, that is oscilloscope and spare parts. We will see spare parts in detail further. These are the tools like serial terminal, serial remote tank, and etc. And this is the help. So let us see this 8 megahertz. Why we have used 8 megahertz? Because for the accurate timing, there are also other options are available like 20, 16, 10 and etc. But for accurate timing we have used 8 only. And for this for the stable and real-time simulation we have taken 31.25 value just for a real-time simulation and nothing else. Okay, now going to the spare parts. This is the main important part. These are the input and output, means here we can get the different components. We have taken ultrasonic HCSR04, this ultrasonic sensors, and potentiometer. This is the potentiometer, and these all three are the ultrasonic sensor. Then from output we have taken LEDs. From these LEDs we are going to use this 4 LEDs. And next is the virtual terminal. We have taken virtual terminal, that is IO virtual terminal, from this virtual function. Now let me show you how to load our binary file. First click on this file, then load binary file. Then we have take the binary file from there where we have saved our binary file. So I have saved here. Now it will take few seconds. See, this is the output. See all the values we are going to see on this IO virtual terminal. See, this is the acceleration pedal, this is the brake pedal, and this is the SOC, that is state of charge, and this is the motor temperature. Let me tell you one by one acceleration. Now the acceleration is less, that is 50 only, and brake is 77, means the vehicle is in the not running state. If I increase the acceleration and decrease the brake, the vehicle will start to run, or it will get started, and here we will see the actual value. See, I have now increased the acceleration, so the acceleration value have increased to 78 and brake has become 18. Earlier it was acceleration was 15 and brake was 77, so it indicates the values. Then SOC means state of charge. If we move this bar up and down, we will get to see the state of charge, means the how much battery is remained for driving the vehicle. Then motor temperature. If we increased this knob, then automatically this yellow LED will get turned on. See, the LED will get turned on. Next is the front, left and right distance. If I decrease the front distance, then these two LEDs get on. This red LED is for collision, CLSN, and these two blind spot detection left and blind spot detection R, means right. These two are for blue and green are for left and right respectively. If I decrease this left, then blue LED will get turned on, and if I decrease this right distance ultrasonic sensor, then green LED will get turned on. Now as we are saying, I have decreased the front distance, then a red and yellow LED is turned on. Now we will see this. See, alarm is showing 3 and fault is showing 5, means there are some fault or the error occurred in the system, that is why it is showing some values. Before it was showing, see, alarm is 0, fault is also 0. If I increase this distance, these LEDs will automatically get turned off, and we will get to see this. See, alarm is 0 and fault will be also 0 in some time. But it will take few minutes. Then this was all about the features or the parameters that we have included in our EV system. So yeah.